Okay, this is the last video in this chapter, and in this video, I'm using the real example. I took this result in the presidential election prediction in 2020, like 2012. At that time, it's Obama's re-election, uh, second term election, and this prediction was from CNN in September, and it's clear. So the point estimator is 50%. Let's just talk about the percentage around Obama. So the President Obama would receive 50% of votes. That's the point estimator. But here, a margin of error is given. So plus minus 3.5% point should be considered as a margin of error. So exactly that's the example of interval estimator. And also sample size is given. 783 likely voters are surveyed or polled. And and one missing information here is the confidence level. But confidence level is 95% because this is the standard. The reason why it is not stated in this graph is because 95% is the standard. So in most cases where like if the confidence level is not given, then you may expect 95% would have been used. Okay, there are two goals like in this example. First, I want to show you what we learned is not just theory. Actually, this graph is made based on exactly same theory we derived today, like in the earlier video. And second, I will connect our theory to the binomial distribution. So it's a little bit like basically the same structure, but it has additional structure of binary distribution. So I will show you how the same idea can be applied in that special case. Okay, so let me start. So first, we'd like to understand the underlying distribution. What is the underlying distribution in this case? I will define random variable x this way. X takes 1 if this person, a randomly chosen person, votes for, say, President Obama, right? Obama, and 0 otherwise. I will explain everything around Obama. So it is a binary distribution we learned in chapter 5. And then what we learned at that time is this. The parameter of interest. So in this example, the parameter of interest we want to estimate is the percentage for this candidate, Obama here, right? Candidate A, I will call him A. So this is the parameter, which is a probability. But the problem here is the parameter we are interested in is a probability, but the confidence interval we learned is based on an estimation for the population mean. So you may think the confidence interval we learned may not be applied for this parameter, but actually, yes, it can be applied because we learned the probability of success equals the mean. So you may call that, you may say the parameter is the mean. We are interested in the mean, or equivalently, we are interested in the probability of success. Does not matter, they are the same thing. So we can use the estimation procedure, which is confidence interval, for the mean. So we developed confidence interval for the population mean and apply that here in the same way because probability equals mean. Okay, then you may apply the same formula. There is no difference. So actually conclusion is pretty simple. But actually you have to be careful in one thing. That's the standard deviation. The standard deviation for the binary distribution was given this way. So variance of binary distribution was p times 1 minus p. So standard deviation was square root of them, square root of that. And then you need to use this standard deviation when you calculate the margin of error. That's the only difference when you apply the procedure to the confidence interval formula to the binary distribution, right? Okay, that means P determines, P is the parameter we would like to estimate, but that again affects the standard deviation. So we need to calculate the standard deviation using this formula. Let's have a look, like a numerical example. Suppose that we are interested in 95% confidence level, and for the parameter P, which can be interpreted as a probability or as a mean. And like it's a separate example, numerical example. Suppose we observe 400 voters and 320 of them will vote for candidate A, right? Then how can we use this information to construct this confidence interval? Let's try this. First, we need to calculate 4 components, right? First, the sample mean is the sample probability of success. Remember, we are handling binary distribution. So X bar, the sample average, is the sample probability. So 320 out of 400 would vote for the candidate. So 80% or 0.8 is the mean or the probability of success. So sample mean down. And second, the standard deviation must be calculated. And we use this formula again, like here. But what is the P? P is coming from the sample probability. Use the sample probability and plug that into the standard deviation formula. We use a separate formula for standard deviation, and then in the end we have 0.4. Okay, we are done with standard deviation too. And then sample size, simple. Square root of 400 is 20. Finally, 95% confidence interval. Always use 1.96, approximately 1.96. So this is the z value used for the interval. Then we are ready to calculate everything. So the margin of error can be calculated with 1.96 times standard deviation 0.4 square root of 400. As a result, 0.0392. Add and subtract this margin of error around the point estimator, the sample average. Sample average plus minus this guy. So that means as a result, from the data, we obtain a confidence interval given by 76 something to nearly 84%. So that means, like in our observation, 80% would vote for this candidate. But due to the error, we have to allow like interval, or think about interval between 76 to about 84, right? Okay, then extending this idea, we would like to reduce the margin of error to 3.5%. 3.5% without changing the confidence level. Then what is the minimum required sample size? Just z is the same because confidence level the same, and standard deviation the same, zero point 0.4, n is unknown, and the margin of error must be smaller than or equal to 0.035. Rearrange and do a simple algebra, then you get 501 point something. That means you need at least 502 observations, the minimum natural number satisfying this inequality. Okay, so if you collect this many data, then you can make the margin of error 3.5%. Okay, then I will have you I will give you an exercise. So now, similar situation, basically the same situation, but data are given this way. Among 400 survey participants, 200 said they would vote for the candidate. What is the uh, margin of error to this estimation? Okay, so if you have finished your algebra, 95% confidence level would imply 1.96. That's pretty much automatic. And then it remains to calculate standard deviation and sample size. Standard deviation is simple because so like the percentage of success is 50%, 0.5. So if you plug in 0.5 here and here, and then take square root, you will get 0.5 as the standard deviation. And the square root of sample size is 20. So combine those numbers, you will get 0.049. That is, margin of error is about 4.9% point. So nearly 5% margin of error should be considered, which is too large, you think. Then I would like to minimize, reduce the margin of error to 3.5% point without changing the confidence level. What is the minimum sample size needed? Your exercise again. Try this. Okay, so assuming you have done, we use this inequality. So 1.96 coming from 95% confidence level, and 0.5 is the standard deviation based on the binary distribution formula, and 0.035 is the desired margin of error, and the sample size is unknown. You rewrite them and you get 784 in the end. So you need 784 samples to achieve this accuracy. And then have a look. 783 is the sample size. So I guess there are some kind of rounding errors. So one is rounding error somewhere. So so exactly I replicated how this survey was designed. So survey was designed intentionally to make the margin of error as at 3.5% point. So the sample size was designed to be 783, right? So you see how exactly the theory is applied in this case. Okay, my last remark is it's a additional remark, kind of redundant, but I get a lot of questions from students who read the textbooks or who took another statistics course. They must have learned two different theories: interval estimation when sigma is known or sigma is unknown. So standard deviation is known or unknown. But as you see, as you can imagine, we are estimating the mean. But how can you know the standard deviation? This is nearly impossible. So I think there used to be a chapter in the textbook for technical purpose. In theory, theoretical derivation requires sigma here, but now I don't think we need to separate them. So especially we needed to assume this because we used many textbooks are based on students' t-distribution theory, which was an old school, outdated, actually, I would say outdated theory. So it is not based on the center limit theorem. It is totally a different theory. But I think these days, center limit theorem can unify all the frameworks. So center limit theorem can be used as used to any case. So we don't need to distinguish these two chapters, and we don't need to know student t distribution. And like in other words, anyhow, student t distribution can be approximated by the normal distribution using the center limit theorem. So so a little bit more discussion, technical discussion about the difference. Student t distribution requires a single observations distribution to be normal, which is very, very strong. But remember, center limit theorem does not require any distribution for the underlying single observation. At that time, like in the previous chapter, we considered dice or unfair dice. Even if the dice was unfair, still the limit is normal. So it doesn't require any distribution assumption. But in student t distribution, if the assumption was correct, it was not an approximation. It is exact analytic distribution for any sample size. But normal distribution approximation is an approximation, assuming large sample size. So it's a trade-off. Like when you compare these two, you have to compare whose assumption is more likely to be true. I would say center limit theorem. Center limit theorem assumes the assumption required for this is large sample size, which is more likely to be true. But student t distribution assumes normal distribution, which cannot be applied to the examples of binary distribution, like presidential election thing. So, and still, the legacy of the student t distribution remains in recent, up-to-date statistics. That's the standardization. So this standardization is coming from studentization. Sometimes we call this studentization, or we call this t-statistics. So t-student was the author name of the statistician who developed this distribution theory, and he named it t-statistics. So this process, standardization, was sometimes called studentization. And anyhow, so I believe student t distribution will disappear from the textbooks in the near future. We don't need it. Like, it's obsolete. It should be obsolete. So this is the difference. I don't know what is standard normal distribution, and so there are two graphs, blue and orange. I guess orange is student t distribution, and blue is standard normal distribution when sample size is 30. As you can see, why we don't need student t distribution. You can approximate the same thing with standard normal. So that's why I do not even mention student t distribution at all. So in case if you wonder why I'm not using student t distribution table, this is the answer. You don't need it. We can just approximate it by standard normal distribution. Okay, so thank you for watching. We have finished estimation theory. So in the next chapter, we will start series of two chapters about hypothesis testing. So it will be a little bit more difficult and complicated. So let's see. See you there. Bye. See you next week.